We are back, episode 2. Last week we introduced the job and went over some of the tactics we'll be using when we establish the survey control network. This week we're going to go over the equipment we'll be using and how to field calibrate that equipment to do our best to remove some of that systematic error we talked about in episode 1. I find sometimes we get too focused on having that 1 second or half second brand new total station, oftentimes using up our equipment budget to do so. But the angular spec of our instrument is just part of the accuracy equation. Prisms, prism poles, tripods, tribrachs, calibration, these can be equally as important, and just because they don't cost $40,000, sometimes we may feel like they don't matter as much. Even though a 5-second total station can absolutely provide better results than a 1-second total station, it may just take a bit more care in the accessory equipment and procedures you accompany it with. Let's spend some time today looking at the less talked about pieces of equipment and, more importantly, how to make sure our equipment is functioning the way it should be. When we're talking about trying to obtain surveyed coordinates with standard deviations of 1/8 of an inch or 3 millimeters, we have to be very deliberate with not only our procedures, not only what total station we're using, but also that accessory gear that goes along with it. This means we can't just use any prism pole, or any tripod, or even any physically demarcated control point. Each of these must be chosen wisely based on what we have available to us and what the needs of the jobs are. I have an entire video dedicated to prisms, so I'm not going to go too deep into the weeds here. If this topic does interest you, I would suggest giving it a watch. But when I'm measuring control points, my prism of choice is a Leica GMP 101. It's small, which means it's fairly transportable. It's nodal, it has a 1 millimeter prism centering error, and its all metal frame is very durable. This prism was actually ran over by a car and dragged for about 20 feet, which wore off the back aluminum nub, scraped it up a bit, completely destroyed the mini Tribrach it was on. But when I thoroughly checked the prism for centering error, there was no effect at all. I try to avoid using 360-degree prisms for control. Why? They almost always come with higher levels of error when compared to round prisms. Are some 360s better than some round prisms? Sure. All prisms aren't created equally, and there are plenty of lower quality round prisms out there. But if you had, say, $1,400 to spend on prisms, you could get one 360-degree prism with a manufacturer listed error of up to 5 millimeters, or 4 GMP 101 prisms for about the same price. 360s have their place, and I love using them for topos, but not when setting control or high accuracy layout work. If I want to set a quick, permanent control point or point I can use to resection off of later, I'll use my auto centering punch to make a dimple on some steel and drop on one of my magnetic Rothbucher prisms. These things are awesome, small enough to fit a couple in my vest and forget about them until I need them, and they are extremely accurate. Plus, it's much more difficult for a dozer to knock down a steel beam with a dimple on it versus them doing their usual afternoon routine of search and destroy on control we set on the ground. After I have my prisms picked out, I then need to figure out what to attach them to. If I'm working on hard surfaces such as concrete or asphalt and have a fairly good line of sight to the ground, I love using these G-Rock mini Tribrachs. They're inexpensive, very transportable, have a small height of target, and they come with 2 spirit level bubbles rated at 1 minute over 2 millimeters. This basically means when the level bubble moves one way or the other in the vial by 2 millimeters, the Tribrach is tilted by 1 minute. If we assume the best we can center that bubble in the vial is plus or minus that 2 millimeters, then that means with a height of target of 18 centimeters, we will be looking at a pole plumbness error of a fraction of a millimeter. Conversely, if we use a carbon fiber topo pole, these are equipped with much less sensitive fisheye level bubbles. The exact rating on them varies from pole to pole, and most usually don't actually list their level bubble sensitivity. I found somewhere between 20 to 40 minutes typical for these style of prism poles. We'll look at a test I ran on this topic in a few minutes. There are a bunch of other manufacturers of these mini Tribrachs. G-Rock I'm sure isn't the best, but they're cheap and they're small. I can usually pick up 3 of these for about $100. The black bag you're looking at now actually holds a GMP 101 Prism and one of the G-Rock mini Tribrachs. You can't beat that for transportability, and that's a big deal on these flyout jobs. In fact, this orange backpack here not only carries my total station, but in just the top section, I have 3 Prisms and 3 mini Tribrachs. Everything needed to run rounds on 3 points simultaneously. Quite the contrast to lugging around 3 tripods, 3 full-size Tribrachs, and 3 full-size Prisms. The caveat with using these is that you need line of sight to about 6 inches off the ground, which can be tricky at times and won't always be doable. If you want to spend a bit more for quality, it's worth checking out the Marksman or the Talisman's Atlas. I haven't personally used either of these, but from what I've seen, they look fairly impressive, but they are not quite as compact. So what do we do if we can't see 6 inches off the ground, and using a carbon fiber topo pole means potentially adding in too much pole plumbness air due to its much less sensitive level bubble? We have a few choices. Leica makes a couple of aluminum prism poles that have 8-minute level bubbles and overall a very high build quality. I've talked about these several times before, and the GLS 12F is my go-to for my main prism pole that holds my data collector. The GLS 13, which I used in this video, is a bit shorter and was actually the only full-size prism pole that fits inside the golf case I use for air travel jobs. I ran a quick test to see what kind of difference height of target and level bubble sensitivity play on a distance measurement. I set up my total station and a nearby control point to measure to. I tested a Seiko carbon fiber topo pole, a Leica GLS 12F, and a G-Rock mini Tribrach, taking 3 distance measurements with each pole configured so that the level bubble was touching the edge of the circle of the fish eye bubble or the first graduation of the spirit level leaning towards the instrument, and then 3 distance measurements so that the level bubble was touching the opposite edge leaning away from the instrument. This Seiko carbon fiber pole had a 5mm level bubble vial circle and a 3mm bubble, so that means the level bubble moved 2mm between sets of shots. The average distance between the forward-leaning shots and the rearward-leaning shots was 26 thousandths of a foot or 8mm when the height of pole was all the way down. It's reasonable to say that we should be able to center the bubble in the vial to about 1mm off center or better, which means that 26 thousandths would get divided by 2 to give us an expected maximum pole plumbness error of 13 thousandths of a foot or 4mm. The Leica level bubble vial circle diameter was 7mm with a 4mm bubble, and the average distance between the forward-facing shots and the rearward-facing shots was 10 thousandths of a foot or 3mm when the pole height was all the way down. When we reduce this distance to the same millimeter of deviation, we would expect someone to be able to center the bubble to. That 10 thousandths of a foot turns into 3 thousandths of a foot or 1mm. And finally, the G-Rock mini Tribrach. There was no clear difference between when the Tribrach was tilting towards the instrument or away. All measurements were in 1,000ths of a foot of each other, just the random error of the distance measurement itself. This is because of the highly sensitive level bubble and the short height of target. I also flipped the entire Tribrach 180 degrees just to see if that would introduce any error, as these spirit level bubbles are more difficult to check and calibrate in the field, and still there was no change. All measurements were 1,000th of a foot or less, a fraction of a millimeter. So we went from an expected maximum of 4mm of pole plumbness error with a Seiko carbon fiber rod to 1mm with a Leica GLS 12 and basically 0 with a mini Tribrach. If I can save a potential of 3mm of error on every measurement by using the GLS 12 over a carbon fiber topo pole, I'm going to do it. That's an easy way to retain quite a bit of accuracy. If you don't have a prism pole with an 8-minute bubble and you need to shoot in control points higher than 6 inches off the ground, the other option, of course, is a tripod and Tribrach. There are pros and cons of taking this route. Centering error of the optical plummet of the Tribrach is usually negligible. It's easy to pick out the center of most kinds of control points using the eyepiece of an optical plummet, whereas when centering with a prism pole tip, you're much better off using a control point with some level of force centering, such as the dimple in a magnail or the intersecting channels of a scribed cross. But when a force centering control point is used, the optical plummet loses its advantage there, as this allows the centering of a pole to be extremely repeatable. Most Tribrachs used for backsights have a fisheye level bubble of 8 minutes, which is the same as what Leica uses on their GLS series of poles. So there's no obvious advantage with Tribrachs when it comes to pole plumbness there either, unless you're using a Tribrach with an integrated spirit level bubble, but those seem to be less common these days. My favorite Prism Tribrach is the one that is paired with the carrier, including the eyepiece and the optical plummet. I can't be the only one that likes these, as the vast majority of Chinese Tribrachs borrowed this design as well. Leica quotes their plummet accuracy of these style to 0.5 millimeter, which beats out the GLS pole option by 0.5 millimeter and gets closer to the mini Tribrach option. A tripod and Tribrach are generally much more stable and sturdy compared to a prism pole and tripod or bipod. I wish I could say I've never had a backsight prism pole fall over on me, but it happens. You can leave a tripod out and have little worry about it getting knocked over by a pedestrian, and being able to use the thumb screws to level it versus bipod thumb buttons is pretty nice for fine-tuning your level. One advantage a prism pole has over a tripod and Tribrach is that you can very easily check and adjust the fisheye level bubble of a prism pole in the field, which we'll look at shortly. But it can be trickier to adjust the optical plummet of a Tribrach in the field. It's still possible, just not as easy and takes quite a bit longer. There is also the very obvious advantage of transportability. A Tribrach, tripod, and prism setup is just too big and too bulky to bring with us for air travel. And even when air travel is not involved, I can carry 3 or more poles and tripods with me pretty easily when setting up prisms. I would not carry 3 full-size tripods and Tribrachs over my shoulder. And since there really isn't an obvious winner in terms of accuracy when using the right kind of prism pole, I honestly don't reach for a tripod and Tribrach backsight setup very often anymore, considering the type of work I do. They're big, heavy, slower to set up. You lose a noticeable amount of vertical accuracy when doing a height of target measure up on a tripod and Tribrach, unless you're using a height hook, versus a GLS 12 that locks into place for an extremely repeatable height of target. If I had a height hook or verticality wasn't an issue and I was staying in one place for quite some time performing precision layout, I would use a tripod and Tribrach if I couldn't see a short HT and use a mini Tribrach. If I'm on the move and I'm traversing along, I'm going to use a GLS 12 and a pole tripod if I can't see a short HT. Sometimes a good prism pole backsight has its advantages. Other times a tripod and Tribrach is better. But the mini Tribrach beats both if you can see that low and there are no cars around to run them over. The total station I've been using for the last year and a half has been my trusted Spectra Focus 35. It isn't necessarily the fanciest or newest total station money can buy, but it is a 1-second instrument. It gets sent in for cleaning and calibration regularly, and I treat it well, so it actually gives me pretty accurate results. And the only reason I would replace it is for an instrument with a built-in camera, which can be really handy for solo total station work. The last piece of the puzzle is the tripod or instrument sits on. I use an ISO 12858-2 heavy rated tripod made from wood. This particular one is made in Germany from a company called Nito. It's been very reliable, is relatively very resistant to drifting or sinking, and is especially heavy, which does take away from our valuable weight allowance when flying, but I feel the benefit to stability and therefore accuracy is worth the extra weight. If you're interested in how tripod quality affects your measurements, I have a dedicated video on that topic as well. I've said it before, and just to reiterate, I have no paid sponsorships in any of my videos. I don't get money from any software or equipment manufacturers I talk about. I have no affiliate links for you. Buy this gear or don't, it makes no difference to me. But if I say I like a piece of equipment, you can believe it's my actual opinion and I'm not getting paid for it. And if I don't like something, I'm going to let you all know about that as well. I've been burned before by believing YouTube reviews of survey equipment that were either paid for or seriously uninformed, and it sucks. There are a lot of mom and pop surveying firms out there doing their best to get by, and I really don't like the idea of shops like that putting out a substantial amount of money for a BLK to go or Pix4D catch, for example, because someone made a video saying you can expect centimeter level accuracy from them. I chose to use our Regal VZ600i terrestrial scanner over our Navis VLX or our RTC 360 for a couple of reasons on this job. I could have used the RTC and might have chosen to do so if I had another full day of time in the field. The VZ is hands down faster than the RTC, especially when a colorized point cloud is required, but the RTC is more reliable than the VZ. I know I can grab the RTC 360 any day of the week and it's going to work, and it's going to work nearly flawlessly. The VZ does create a fantastic data set and also has some advantages on the processing side of things, which we'll look at in episode 4, but it's buggy, at least in my experience. This particular data set wasn't too bad in the field, although I had 2 scans fail randomly and the field registration quit for no apparent reason on me halfway through scanning. Luckily, I've seen both of those issues before and knew what to keep an eye out for and how to fix them. And since I'm still getting to know the VZ, I can only assume that I will get to know its quirks and in time it will be less of an issue. But at the same time, the RTC gives me much less grief in the field and in the office, if I'm being honest. One of the deciding factors to use the VZ here is it does allow me to window a specific area out in the scan and rescan that area with a much higher density of points. This came in handy on those rooftop scans that were separated by a relatively far distance. And the Regal being a time of flight LiDAR scanner versus the RTC using a phase shift measurement means the VZ is better suited for those longer range rooftop scans as well. So what about the VLX? Being that we needed a 1/4 inch accuracy across the entire site, I would not have felt comfortable using our VLX or any SLAM sensor for a project that required that level of accuracy. It's no secret a tripod mounted static scanner is going to be more accurate than a SLAM scanner. Also, the VLX is much bigger, which means checking it on my flyout jobs, and that always makes me nervous considering how airlines handle checked baggage. It's Sunday afternoon and we just landed in LaGuardia Airport in Queens, New York. After a quick shuttle to pick up our rental car for the next 3 days, we made the 1.5-hour journey from New York to Connecticut, where we arrived Sunday afternoon at about 3:30 p.m. to a vacant construction site. My eyes lit up when I saw we had the entire site to ourselves, as this is a huge advantage for us to start setting the framework of our control network, as we didn't have to worry about vehicles, equipment, or people moving into our line of sight or stopping to ask us questions as we traversed around the building. The first step, as soon as I get on site for the first time, is to do an initial site walk to start to visualize how I want to carry out the survey. I'm looking for locations where I can set my traverse hubs that will be relatively safe from vehicles and equipment, that not only have an unobstructed line of sight now, but are also unlikely to be blocked by parked cars or equipment in the future, preferably on stable ground, to reduce the amount of settlement the tripod the instrument is set up on will experience. After I do my first lap of the site, I start my second lap where I start demarcating my traverse hubs. I usually prefer scribe crosses in concrete, but if I'm in a location where it's not too hot, mag nails on asphalt work great as well. On a quick side note, the scribe I use to set crosses in concrete is a Richards laminate cutter. I get asked about it all the time. It's awesome. I can't recommend it enough. I think you can get them for around $10 a lot of the time. It has a carbide tip. This one is probably 5 years old at this point and still works like the day I bought it. They can be a little tough to find here in the US, but they're everywhere in Canada, and I found a couple resellers down here as well. Down in Florida on a hot day, it's pretty surprising how fast your instrument will start to sink and drift on asphalt. Lucky for us, we had very mild weather during this project and we didn't have to worry about this at all. If I absolutely need to set a control point in soil, I will either use a hub and tack, spike, or rebar, but I will use a center punch or paint pen to mark a defined center point on those last two to help with centering repeatability. When setting traverse hubs, it's handy having 2 people, so you can have one person stand on the setup point and the other can thread the needle, if necessary, to set hubs when the line of sight may be a narrow gap between obstructions. When I'm working solo, I will usually level my instrument over the setup point and then demarcate my backsight, foresight, and common points, all while the instrument is in place and set up, so that when I'm scribing or hammering in a control point, I can make sure I can see the total station, and I usually just set the hubs as I go. After we set our 4 main traverse hubs and all of our common points, it's very important that before I start making any measurements, I run through all of the field calibrations on the data collector for the total station, make sure the rod level bubbles haven't been disturbed, and check the tripod to make sure that none of the fasteners have worked themselves loose. All of the equipment just went through some serious travel where it's absolutely possible they may have experienced a few bumps along the way, and some fasteners can now be loose. I'll start out by checking over the tripod to see if the clamps holding the legs or the plate attaching the Tribrach rest to the legs have loosened up at all. These rarely need adjusting on this particular tripod, but I've had others in the past where it's an ongoing issue. If you see the same issue, give some blue Loctite a try and it should fix it for you. I like to set the tripod head tension so that I can lift a leg up so that it's parallel with the ground and it has just enough tension to stay there, but it doesn't take much force to push it back down. In the leg clamps, I like to tighten so that it takes a fair amount of resistance to close the clamp, but I'm not stressing the tripod by having to really push too hard to clamp the legs. Next, I set the instrument up on the tripod over the control point I'm going to start my traverse from and wait for it to acclimatize if necessary. In this case, it was not needed as all of our gear had been sitting in the vehicle for the past 2 hours that neither had AC or heat on. Once the instrument is leveled, the first calibration routine I'm running through is the compensator calibration to make sure the dual axis compensator of the instrument is calibrated properly. You can also do a quick check to see if it is in calibration by having the level bubble screen open on the data collector, noting the values of the trunnion and sighting axis, and when you rotate the instrument 180 degrees, you should see the same values but with the opposite sign. So for example, if I'm seeing positive 4 seconds in the trunnion axis and positive 2 seconds in the sighting axis, when I rotate the instrument 180 degrees, I should see negative 4 seconds in the trunnion axis and negative 2 seconds in the sighting axis. Now, the next 2 error sources that the calibration routine runs through should theoretically be averaged out by dual face measurements, which we'll always do when performing high accuracy control networks, but I still like to run through them regardless, and these are a no-brainer when doing high accuracy layout. I'm talking about the collimation and tilt axis calibration routines. For the collimation calibration, you sight a distant, well-defined target on both faces, preferably multiple times on each face, and the data collector calculates the difference between the averaged pointings of both faces, both horizontally and vertically, and automatically applies it to future measurements. So for example, if I'm pointing at a target 100 meters away on face 1 and read a horizontal direction of 0 degrees and a zenith angle of 90 degrees exactly, then flip faces and read a horizontal direction of 180 degrees, 0 minutes, 10 seconds, and a zenith angle of 90 degrees, 0 minutes, 6 seconds, the instrument will apply a collimation correction of positive 5 seconds horizontally and positive 3 seconds vertically to future face 1 measurements, or the same values but with the opposite sign to future face 2 measurements. The tilt axis calibration works in a very similar fashion. The difference is that the well-defined target must be at a fairly steep incline, as tilt axis error has no effect at the horizon or a zenith of 90 degrees, and the influence it has on the measured horizontal angle grows as you tilt the instrument up or down away from the horizon. And if the tilt axis error has no effect at the horizon, the correction cannot be measured at the horizon. And wrapping up the field calibration routine for the instrument, we have the autolock or ATR collimation calibration. This error is not removed by dual face measurements, therefore you really don't want to skip this calibration routine. I do have plans to make a dedicated video on autolock or automatic target recognition of total stations, so I won't go too deep into the adjustment. But for now, for the sake of context, this routine is basically calculating and compensating for the deviation between the optical line of sight of the instrument, aka the crosshairs of the telescope, when pointing at the center of the prism, and where a robotic total station's CCD array that is part of the auto lock system is determining where the center of that prism is. The auto lock system on a robot emits an infrared beam, and when that beam is reflected by a prism, there is a sensor inside of the total station that captures that reflection and calculates the location of the prism center. If you've looked through your robotic total station when using auto lock and noticed the crosshairs aren't pointing at the center of the prism, this is because a robot will approximately point the instrument at the center of a prism just close enough to accurately take a picture, so to say, of where the prism is and determines the center of it and calculates the offset between the crosshairs and the calculated center of the prism and applies that offset to the angle measurement. When we run through the autolock calibration routine, we are allowing the autolock to take that picture of the prism we just talked about. We then manually point the crosshairs to the center of the prism to determine if the two measurement methods agree, and if they don't, an adjustment is calculated and applied to future measurements, very much like the collimation calibration. Now that the instrument has been calibrated, the tripod it sits on has been checked and adjusted, we need to check that our prism pole level bubble hasn't gone out of calibration. If I'm in the office, I have a prism pole adjusting rig that works great, but in the field, what I'll do is I'll level up the pole with a bipod or tripod about 10 to 20 feet away or so from the total station. Sight the tip of the pole, then tilt the instrument up until I'm looking at the center of the prism. You'll want to make sure your auto lock is turned off when doing this, and also being careful not to touch the horizontal angle knob of the instrument when tilting up. If we were zeroed when pointed at the tip, we want to be zeroed when tilted up. If the crosshairs aren't centered on the prism, then we know the prism pole isn't leveled properly even though the level bubble is saying that it is. Therefore, we must adjust the level bubble vial. Before adjusting the bubble, I'll rotate the pole 90 degrees and turn the prism back so that it's facing the instrument to check the level bubble adjustment perpendicular to the axis I just checked. To make sure the rod tip doesn't move while rotating it, tilt the instrument line of sight back down and verify you're still sighting the pole tip. It can be handy to use a mag nail to hold the prism pole in place when doing this calibration. If the crosshairs stayed on both the tip of the pole and the center of the prism the whole time, your prism pole level bubble is good. If you find you're not centered on the prism when tilting up, which was the case when I ran through this routine on this job, we must adjust the level bubble vial. Have a coworker very slowly tilt the pole over using the tripod or bipod thumb buttons until the center of the prism is over the crosshairs of the instrument. At this point, the level bubble will not be centered in the vial. Now use an Allen key on the set screws on the underside of the vial to adjust the level bubble until it is centered in the vial. Rotate the prism 90 degrees and repeat the process, and finally rotate it once again to make sure it's still in adjustment in the original configuration. Repeat if necessary. A quick note when adjusting the set screws that hold the level bubble vial in place. You can't just keep tightening one side indefinitely. If you notice the side you need to pull down is getting tight and you still need to adjust it more, loosen one of the opposing screws and you should free up some more adjustment in the one that was previously maxed out. Another method of field calibrating a prism pole, which is much easier when working alone, is to level up your total station high above a well-defined control point like a mag nail. Then using a pole tripod, level your prism pole underneath the total station with the prism off. When you look through the optical plummet of the instrument, instead of seeing the mag nail, you will now see the center of the prism pole. If it isn't centered, tilt the prism pole with the tripod until the top of the center of the pole is under the instrument's plummet. Then adjust the level bubble vial until the bubble is centered. The plummet of your total station creates a plumb line through the top of the center of the pole, through the center of the shaft of the prism pole, and down into the center of the mag nail. And worst case, if you get to the field and notice your level bubble is out and you have no tools to calibrate it, you can still get accurate results by taking a number of observations to the pole in its usual configuration, then rotating it 180 degrees and then taking an equal number of observations with the pole reversed. This works because if the pole is out of calibration and leaning northwest by 3 millimeters on a particular observation, when it's rotated 180 degrees, it will be leaning 3 millimeters southeast, and the two sets of observations will cancel the pole plumbness error out. very similar to how dual face measurements cancel out collimation errors. This same process can be used on a tripod Tribrach if you are unsure of its calibration. That's going to wrap up the second episode of this mini-series. 2 episodes and we haven't even started to collect any data yet. We're taking our time getting there, but I promise it's coming. Everything we've covered so far is extremely important when dealing with high accuracy total station measurements. If you're not employing any of these tactics yet, my recommendation would be try out a traverse with methodology you use and are comfortable with, then repeat it with some of the tactics we've covered here and compare the results. Don't take my word for it, do your own testing. And if you do, please comment and let me know how it went. And to that end, if you have any questions, comments, or disagree with anything that was said, please don't be afraid to speak up. It's always great to get some discussion going, and I'm here to learn from colleagues as well. In the next episode, we're finally going to collect all of our data, run through some survey data processing, and see if we actually were able to hit the accuracy spec for our control network. I promise no numbers will be fudged, and we will see if the extra effort we put into our measurement scheme was worth it or not. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.